Hello, my name is Isaac Chakai, and today I'll be presenting on deep neural networks and sequential Monte Carlo for inverse manipulator kinematics. To begin, while closed-form and iterative numerical solutions exist for the inverse kinematics problem, both of these solutions suffer at kinematic singularities where multiple solutions may be obtained for the same desired end effector pose. Meanwhile, deep neural networks and sequential Monte Carlo methods have both been proposed to mitigate this issue. In this work, two different manipulators were used. The first one was a planar manipulator, and the second one was a 6-degree of freedom manipulator shown in Figure 1. To describe the kinematics of both of these manipulators, the Denevitt-Hartenberg convention was used to chain a series of homogeneous transformations between consecutive joint coordinate frames to achieve a final end effector pose. The inverse kinematics problem thus requires a functional mapping from the end effector pose to the original joint angles to achieve the pose. This functional mapping is slightly modified to improve approximation accuracy as well as to avoid the kinematic singularity problem by including current joint angles and current end effector pose. To briefly review, deep neural networks are composed of an elemental deep artificial neuron, which is composed itself by a set of linear weights which are fed to a sum function, then fed through a nonlinear activation function to mimic the functional architecture of a real biological neuron. These artificial neurons can be stacked and chained together to form what are known as deep neural networks, which are capable of approximating nonlinear multidimensional functions. These networks are optimized using backpropagation algorithms, which update the linear weights in each iteration. Meanwhile, sequential Monte Carlo methods approximate an expectation distribution by randomly sampling state estimates from a belief distribution. These state estimates are then fed through the nonlinear kinematics model to produce new state estimates. These new state estimates are then measured with respect to an importance weighting function, which updates the belief distribution. This series of operations is iterated over, hence the sequential Monte Carlo name. The final state estimation is thus taken as the weighted average of all the sampled states. Thus, the proposed inverse kinematic solution utilizes the initial estimate of the deep neural network and then is refined by the sequential Monte Carlo method. It is shown in results that while the deep neural network is capable of producing a good approximation and a good first guess for the sequential Monte Carlo method, the sequential Monte Carlo refinement is capable of reducing the error for both planar and 6-degree of freedom cases by an order of magnitude. These errors were measured from a path tracking task shown here. It can be shown that for both the planar and the 6-degree of freedom case, the approximated inverse kinematic solution is very accurate. Thus, the new pose from the inverse kinematic solution can be reused for the next iteration. In conclusion, while deep neural networks are capable of adequately approximating the inverse kinematics of 6-degree of freedom and planar manipulators, sequential Monte Carlo refinement greatly reduces the approximation error, partially due to the good first guess from the deep neural networks. Given the solution does not require significant theoretical development in either the deep learning case or in the iterations of the sequential Monte Carlo method, this proposed solution aims to generalize well to any manipulator inverse kinematics problem, and further work can explore the use of this method with redundant manipulators and manipulators with joint offsets. Thank you very much. Here are my references.